As the name says, we are going to talk about gases in this topic. In case of gas, you don't really have a fixed volume. If you have a hole in a tire going through the tube, then the air leaks and goes everywhere. It's not like solid which you can hold. It's not also like liquid which also you can hold, at least to some extent. Gas just spreads. So we cannot really talk about the fixed volume of gas. We cannot talk about fixed volume of gas because it spreads. If you take some gas in a small container, it will spread in that small container. If you take exactly the same amount of gas in a big container, it will spread in that big container also. It's not like liquid that if you take a small container, then liquid will fill up to this point, and if you take a large container, then liquid will fill up to only this point. In case of liquid, this is what happens because the volume of the liquid is fixed. 2 liters of milk, 5 liters of milk, we can talk like that. But in case of gas, it is the container which will decide the volume. So now I must have a closed container. I can keep the same amount of gas in this container also. I can keep the same amount of gas in that container also. Gas will just spread. Whatever small amount of gas I have, it will just spread. So one very important thing about gas is volume of gas. What is the volume of gas then? If it is just spreading anywhere, then what is the volume of the gas? So, volume of the gas is the volume of the container. It's the volume of the container. If gas is in a big container, the volume of the gas is also big. If gas is in a small container, the volume of the gas is also small. Very interesting concept. Volume of the gas is the volume of the container. Now, if you could increase the pressure, let's say instead of fixed, I make it movable. Now imagine some gas particles there, and that piston is in your control. You can move it up, you can move it down. When you move it up, obviously you are increasing the pressure. That would reduce the volume available for gas. Volume available for gas is the volume of the gas. So that's a property. Homogeneous mixture with other gases. Gases mix very well with each other. There are very few complications. Liquids also mix with each other, but there are several complications. When you use paint, you never wash your hands with water hoping that the paint would go. right? I'm talking about the real paint, not whitewashing type of thing. But if you use turpentine, then that paint really goes, because the paint dissolves in turpentine but does not dissolve in water. Water mixes with many other liquids, but if you talk about gases, then the mixing is just excellent. What we breathe is not just oxygen. What we breathe is mostly nitrogen and oxygen combined. And if there's a perfume bottle kept in the room, then along with nitrogen and oxygen, and of course there are other things like some water vapor present in the air, perfume vapors are also going. Perfume vapors mix very well. They mix so well that even if perfume bottle is kept at one end of the room and you enter the room from the just opposite end, you can smell it if there is enough time, if the perfume bottle is kept for enough time and if it's open. You can smell it from a distance. Mixing is simply excellent in case of gases, mixing of a gas with other gases. Now that has to do with, mixing has to do with particles entering empty spaces. Particles entering empty spaces. If two particles are like these and there is so much of space, then third particle, fourth particle, they can easily enter. So when you take breath, all these particles pass. Gap between particles is quite a bit, and that's why diffusion is so good, mixing is so good, and that's why you are able to compress the gas so much. Try to compress the solid. Try to compress the solid and see if you can. Now don't tell me that a sponge can be compressed. Yes, sponge can be compressed, and even tennis ball can be compressed, or different types of balls can be compressed, but that's not solids we are purely talking about. When you compress a tennis ball, are you compressing 100% solid? No. Inside that shape, there is a lot of air. So when you compress tennis ball, it's not 100% solid that you are compressing. There is good amount of air inside it. Here, you have gas, apply force, piston moves down, gas is getting compressed more and more and more and more. If you try to do this type of thing with solids or with liquid also, they don't like to get compressed, solid or liquid. Now, if you say that I would look into every particle of the gas and I would add up the molecular volume. If you say I would add the molecular volume, then that's a tough job. That's a tough job. Molecular volume is not called volume of the gas. Molecular volume is generally very, very, very small in comparison to the volume of the container. Most of the space is free. Move your hand easily in air. You perhaps won't even notice any resistance. Try to move your hand in water and see how much resistance you feel there. And when you move your hand in air, see how much resistance you feel here. very less resistance. The particles of air, if you count one by one and start adding their volume, one particle's volume, imagine it to be spherical in shape, 4 by 3 pi r cube. Another molecule or particle, 4 by 3 pi r cube. If you keep on adding like that, all of the sum you will find to be, generally speaking, 0.1% of the volume of the container. Whenever we talk about volume of a gas, we don't talk about molecular volume summation. Molecular volume summation is fixed. Molecular volume summation is fixed. That is not what we mean by volume of the gas. Volume of the gas means the whole space where gas has managed to spread. So it is the volume of the container. Not this plus this plus this, not that molecular volume. So I hope that particular point is very clear about volume. You hear a lot about pressure. What exactly is pressure? Pressure, I think you have introduction to concept of pressure. Pressure depends not only on the force, pressure depends on the area also. Like a needle can give you more pain than somebody with thicker base. Somebody with thicker base, if you apply the same force, right? In fact, if you apply a lot of force, the needle can even penetrate, while a thick base won't be able to penetrate. That's the idea of pressure. It is not just the force that you apply, it is also the base area, the area under consideration, that area. That's why nails have points. If a nail does not have a sharp point, it won't be a good nail. It will be harder to penetrate if the nail does not have a point. Pressure has to do with area. Pressure is force per unit area. That means smaller the area, more pointed is the surface. Same amount of force, if you apply, even on both the cases, smaller area, larger area. The smaller area will give you higher pressure. Smaller area will give you higher pressure. Now we say there is atmosphere above us. If we are pulled by earth, then shouldn't atmosphere be pulled by earth? It should be, because if it were not pulled by the earth, then it would escape. Why would earth have any atmosphere at all if it is not pulled by the earth? Somebody is holding it with earth. So if we are pulled by the earth, then atmosphere is also pulled by the earth. And if you stand and you experience pull by the earth, then that air above you, that should also experience pull by the earth. If you have done the swimming, or if you ask somebody who has done the swimming, then as you go inside water, the deeper you go, greater is the pain in your ears. The height of water above your ears, if that height is more, pain is more. Fluid, whether liquid or gas, they are all pulled by gravity, gravitational force, Earth's attraction. So if anybody is below them, water everywhere, simmer is somewhere here. If anybody is below, then Earth is pulling that water with gravitational force. That is the reason why that person feels pain. So imagine somebody sitting over you. It's just like that. Imagine this water sitting over you. Imagine the atmosphere sitting over you. What will happen? Now you get accustomed to living in atmosphere, so you don't feel uneasy. And you don't feel uneasy also because it is all thin air, such low density of air. But going deeper inside water is going to give more and more pain. Water is having much higher density than air, of course, you know that. So, pressure is force upon area. Why there is force? In case of atmosphere, why there is force? Because there is earth, there is force. If gravity were not there, force would not be there. Now just visualize at where you are sitting 1 meter by 1 meter area, not big, 1 meter by 1 meter. 1 meter by 1 meter area, and mentally raise it upper and upper and upper till there is atmosphere. Till there is atmosphere. So 1 meter square area where you are sitting, and then upper and upper and upper, you just keep on going higher and higher and higher because atmosphere is like that. Imagine the weight of the air contained in that column. 1 meter square at the base and that enormous height. Weight of that air. Weight of that air. 10 to the power 5 Newton is the force that this air column exerts. Now why did we choose 1 meter square area? Because force per unit area, this is a unit area. This is the unit area, 1 meter square. So that means whatever is the force, same would be the pressure. That means 10 to the power 5 Newton per meter square. That is the pressure you experience. That is the pressure under which we live. If you are going inside the swimming pool, now pressure has a property, we will talk about it in hydrostatic topic, but you can know about it right now. Pressure has a property that it gets transmitted. So if you are inside the swimming pool, then the air will still do its job. If somebody is sitting at your shoulder and on the shoulder of that person another person is sitting, then won't you effectively feel it? You will certainly feel it. Somebody on your shoulder and on that person's shoulder somebody else. You are inside water and water is inside atmosphere. Pressure gets transmitted. So the pressure that you feel inside water is the sum of the two pressures. Pressure applied by the water above you plus pressure applied by the atmosphere at water's surface. So when we say this is only due to the atmosphere. This is only due to the atmosphere. If you are handling a situation where you have a liquid like this and you are studying this point, then this pressure will be there plus pressure due to this liquid height column. The 2 will be added in that case. This Newton per meter square is called Pascal. So 10 to the power 5 Pascal, which is 100 kilopascal, that is the atmospheric pressure. Here you can visualize, look at the mass. It doesn't sound much. Imagine the height, so much height, and 10 to the power 4 kg is not much. One small car is around 1000 kg, one small car. So 10,000 kg, just 10 small cars. That's it. That's because the density is so little. Density of air is so little. And height is so much. Volume would be enormous. There is another unit called ATM. So what we saw here as 10 to the power 5 Pascal, that is also called as 1 ATM. Unit is something you have to be very careful about in chemistry. Physics is more comfortable in the context of units. More SI system is in use in physics, but in chemistry that's not the case always. Unit is something that we have to be very careful about in chemistry. 1 ATM, this is not SI unit. SI unit is Pascal. But 1 ATM is equal to that. It is the just atmospheric pressure, 1 ATM. Now, a little bit of hydrostatics is going to be important for us in this topic. I talked earlier about something inside water. If something is at H depth below the surface, then the pressure that water would apply here would be due to this height. And it is given by density of water, in fact any liquid. Why talk about water only? Any liquid. Density of that liquid, height, G. Look at G. This is the key. If you don't have G, there is no problem. I mean, no such pressure will be there. It's all because of G, gravity. So that would be the pressure at this point due to only this liquid. But as I just told you, pressure is always transmitted. So if atmosphere is here, if it is here, sometimes we deal with closed systems also, which are not exposed to the air directly. If I can close it, I would not expose it to the air. So air would not be able to apply pressure. But if it is open, air is in contact and is above, then pressure due to air will be transmitted. And if that is 1 ATM or 10 to the power 5 Pascal, then that needs to be added to this. to find the total pressure at this point. So this formula comes from hydrostatics. H times density into G. Now coming to this point, atmospheric pressure is measured with barometer. You would see that the favorite liquid in such cases is mercury. The favorite liquid in such cases is mercury. And one of the prime reasons is that mercury is very dense, very dense. To give you an idea, in comparison to water, mercury is 13.6 times more dense. And mercury rises due to pressure. You are trying to measure atmospheric pressure. And how do you do that? You look at the mercury height. Mercury rises. Now why does it rise? We will discuss all that. Right now you just take it that because of the atmospheric pressure, mercury rises. How much? If outside pressure is 10 to the power 5 Pascal, then mercury would rise by 76 centimeters. 76 centimeters is how big? 1 meter you can imagine, right? 1 meter. 3/4 of a meter roughly. Not very big, but still it's a significant height that the liquid is rising by. Nearly 3/4 of a meter is the height that mercury rises by. Now, because of this, 76 number is very important for us. 76 number is very important for us. In fact, many times we say that the pressure is 76 centimeters. Now, centimeter cannot be the unit of pressure. But when we say pressure is 76 centimeters, it means 76 centimeters is the height of the mercury column. So one can convert that to appropriate unit if one wants to. Now, as I said earlier, units are going to be one of the key things in this topic. So when we say 1 atm pressure, it means 76 centimeter mercury column or 760 millimeter mercury column or 760 torr. You must make note of all these things. 760 torr. So what is torr? Torr is 1 mmHg. Torr is the pressure corresponding to 1 millimeter height of mercury column. Now earlier we had a number with us which was an approximate number. It was 10 to the power 5 Pascal. Now you have a more accurate number. This is 10 to the power 5, but you can see that it is more accurate, 1.01325. This also you need to make note of. So what is ATM to PA conversion? 1 ATM is 1.01325 into 10 to the power 5 Pascal. Which unit is the bigger unit, ATM or Pascal? That's very good. Now I'm moving towards that point. How does it rise? I mean, why does it rise? Height. Now you can see the setup, experimental setup. Experimental setup is very simple. You have mercury in a container. Now why mercury? I told you density is a key point. And I will tell you one more thing. Look at this formula. Why density is the key thing? Why density is the key thing? Because if density is more, to get the same pressure, if density is more, to get the same pressure, you need small heights. Even small is not very small, 3/4 of a meter. But quite okay from laboratory perspective, 3/4 of a meter is no problem. But just think, if we use water for this experiment, how high will it climb? Water is 13.6 times less than. That means G is not going to change. That means H should be 13.6 times more to measure the same pressure. 13.6 times more to measure the same pressure. Think about it. 3/4 of a meter multiplied by 13.6. Will it really be practical from laboratory perspective? Think about the height of the roof in a room. So Mercury's high density gives us lower heights, convenient to handle. Now what is the concept? Why does it rise? You have mercury in a container. Now keep it open to the atmosphere. Atmospheric air is pushing it down. It's pushing it down. At this point, the pressure is equal to the atmospheric pressure, PA. Pressure is going to be the same at the same height everywhere. Whether I take this point, or I take this point, or I take this point, any point I take anywhere on the surface. I mean, it should be at the same height. I should not go deeper. I should be at the same height. That means I will be on the surface. So any point I take on the surface of the liquid, the pressure is exactly PA. So why does mercury have to climb up? Why does mercury have to climb up? Because if at this point you want pressure to be PA, pressure has to be PA from the rules of hydrostatics. At the same height level, any point you take, it should be at the same pressure with respect to anybody else. So it means if I take a point here also, it will be at the same pressure at this point, and this point is at atmospheric pressure because it is directly exposed to the atmosphere and it is at the surface. Now how do I get PA there? That point I have chosen is inside the tube. This is the tube which is closed from the top This is a tube which is open at the bottom. Open at the bottom, closed at the top. Where is the atmosphere above it? I mean, there is atmosphere above it, but it is not pressing the liquid. Atmosphere is not here, inside it. There is no atmosphere inside the tube. There is no atmosphere inside the tube. So the question is, how to get 13.6 there? 13.6 is obtained when somebody presses from the top. Who is there to press from the top inside the tube? Nobody. Right now, nobody. But then, if it is going to be nobody later also, then how will that number of 13.6 come? If there is nobody inside the tube, 0 should be the answer. Vacuum can give you 0 pressure, no pressure. But the pressure is PA. So, mathematically speaking, to make it PA, you need some height there. You need some height there. And who else can get you that height? That is closed from the top, it is open from the bottom. Who else can give you that height except the mercury rise taking place inside it? When mercury rise takes place, now we can explain how the pressure there can be PA. Now we will say, okay, there is no atmosphere here, fine, but there is mercury from here to here. And if that mercury is there, there will be pressure at this point. And that is how we can say that PA can be there. So I hope it is clear now why mercury has to go up. Any questions if you have, just let me know. Okay, we stop at this point.